All right, just a quick note about something called the binomial theorem. And this is nice. I'm just going to do some examples and then I'll write down what's happening here. So it basically is about taking powers of binomials. So if we look at something like x plus y cubed, well, what is that? That's x plus y times x plus y times x plus y. So what's going on here is as follows. Well, when we multiply this out, we're using the distributive property. So we're doing every combination of an element from our first bracket, an element of our second bracket, and an element of our third bracket. So if we look at this, let's look at every combination that has 3 x's. So we have 3 x's, 1, so we're choosing this guy, and this guy. So there's one choice. But it changes a little bit when we look at different combinations. How many ways can we choose 2 x's and 1 y? Well, we can choose, let me write it out again, just to have a little more room. X plus y, x plus y, x plus y. Well, we could choose these 2 x's and this y, or we could choose these 2 x's and this y, or we could choose these 2 x's and this y. So we get 3 different ways we can get the term x squared times y, x times x times y. And similarly to those, we get 3 choices where we can have x, y squared, picking 1x and 2 y's, and, well, 3 y's is just y cubed. So in total, well, we have that x plus y cubed is x cubed plus 3x squared y plus 3xy squared plus 1y cubed. And we can even think, I'm just going to write this in here, there's like a y to the 0 here and an x to the 0 there. So what's happening? Well, really, here we're counting the number of words of the form x, 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 and there's exactly 1. Here we're counting the number of words of x, x, y. I should say not words, but arrangement of. So here and here, I want to say arrangement of. Arrangements of the letters xxx, xxy. There's 3 ways to arrange xxy. And similarly, there's 3 ways of arranging xyy. And there's 1 way of arranging YYY. So that's what's kind of going on here. So if we look at this term here, this xxy, well, how many ways are there arranging that? Well, there's 3 factorial, and we only have 2 different letters. We have 2 x's and 1 y. So this is 3 choose. We can even say choose 1. It doesn't really matter, because remember, 3 choose 1 is the same as 3 choose 2. We're either choosing our x's or choosing our y's. You're going to look at it in either way. So, in general, we get that x plus y to the power n, well, we have, let's look at it like this. So we have n, choose 0, because remember we have 0 y's here. So we're counting this, we're thinking of this as the number of y's in our word. So that's kind of the r in our n choose r. So that is x to the n, and I'll write it, and I'll leave it like that, but remember there's a y to the 0 here. Well, now there's 1 y, so we have n choose 1 ways of arranging n minus 1 x's and 1 y all the way to n choose n ways of arranging n y's, but remember there's 0 x's here, and you can write that if you like in summation notation. So that is from I equals, well, let's say from r equals 0 up to n, it's going to be n choose r x to the n minus r y to the r. So remember, this here tells us the number of arrangements of r y's and n minus r, the rest of them, x's. And remember, the reason we're doing that is because when we use the distributivity to multiply, we pick one term from each of the binomial brackets. So if we want to count how many ways there's 2 x's and 1 y, then kind of any arrangement of x, x, y gives us a new way to multiply. So that's what's going on here, and this is called the binomial theorem. So this is the binomial theorem. All right, so let's look at an example. Let's expand. Oh, let's just find the coefficient for, let's do this one. Let's do x to the 4 y cubed and x to the 5 y to the 4 in the expression 3x squared plus 2y to the 5th. Okay. Well, here's the thing. So let's look at this. All right, we're thinking of this whole thing, this 3x squared as our x, and this 2y as our y, using the notation in the definition. I know it's kind of a repeat notation, so it's not particularly precise, but just to match it up with the previous definition, that's why I wrote it like this. But anyway, using the binomial theorem, we get that 3x squared plus 5y to the 5th is going to be the sum from r equals 0 to 5 of n choose r times the x bit, 3x squared to the n minus r, times the y bit, 2y to the r. Let's simplify this a little bit. So we still have our sum, r equals 0 to 5. We still have this n, choose r. But I'm going to split this up into 3 to the n minus r. And then I have x to the 2 times n minus r, just expanding out using our rules for exponents here. And then this will be times 2 to the r y to the r, just expanding that out. So we get, and I'll still write in the indices, why not? And choose r. And so let's combine these a little bit. So we have 3 to the n minus r times 2 to the r times x to the 2 n minus r times y to the r. So, well, we want, for the first bit, we want the coefficient when y has a power of 3. So r is 3. So in this sum from 0 to 5, we want the term where r is 3. So the coefficient of x to the 4 y cubed is going to be when r equals 3. So it's going to be n choose 3. But we know n is 5. So even up here, I wrote n. But we're thinking of these as 5. Because n is 5 in this case. And same here. This is 5. This is 5, etc. All our n's are 5. So wherever I wrote n, I meant 5. So let's write it 5 here. 5. Ooh, choose 3. Times, well, what do we have here? We have 3 to the 5 minus r in this case is 3, times 2 to the r, 2 to the 3, and then we have x to the, let's make sure this works, 2 to the 5 minus 3, and y to the 3. And this makes sense. So 2 times 2 is 4, so this is x to the 4. So we have the right term. So this is 5 cubed, and this bit isn't the coefficient bit, by the way. I just wrote that in just as a check that we do indeed have the right term. So we have 3 squared times 2 cubed. We can simplify that in a bit. And this isn't our coefficient bit. This here is our coefficient. We have x to the 4 y cubed, so that's what we want. Okay. And so let's simplify this. 5 choose 3, so that's 5 factorial over 3 factorial, 2 factorial. And you guys can check that this is indeed 10. So we have 10 times 9 times 8. X to the 4 y cubed. And you can check this is 720 x to the 4 y cubed. So our coefficient is 720. Let's go back up to that top example, or the top here for the second example. If we look at this, we want x to the 5th, y to the 4th. But notice here, if we plug in 4 into here, we're going to get an x power of 6, not 5. So let's check that. So note when r is 4, x to the 2 times 5 minus 4 times y to the 4 is x to the 2 times y to the 4. So there is no x to the 5, y to the 4 term. And if there's 0 of those terms, thus the coefficient is 0. We have no x to the 5, y to the 4 terms in our expansion. So hopefully that is okay there. And let's do one final example. Let's find the coefficient of x to the 16 in the following. And the expansion of 2x squared minus x over 2 to the 12. Okay, this one's going to be a little bit different because we have the same variable. Here we have an x squared and an x, so we'll get a little bit of simplification happening. So let's simplify this as much as possible. So 2x squared minus x over 2 to the 12, well, that's going to be the sum from r equals 0 to 12 of 12 choose r. The first term, 2x squared to the 12 minus r, and the second term, x over 2 to the r. Let's simplify that as much as possible. So we have our sum, 12 choose r, and this becomes 2 to the 12 minus r times x squared to the 12 minus r, so x to the 2 times 12 minus r, times 1/2 to the r, and x to the r. Let's simplify this just a little bit more. 12 choose r, and this will be, let me write this 1/2 to the r. This is the same as 2 to the minus r. So we have 2 times 12, or 2 to the 12 minus r times 2 to the minus r. So we're multiplying things with the same base, so we'll just add their exponents. So this becomes 2 to the 12 minus r is 12 minus 2r. And then here, we can look at this, if you like, as x to the 24 minus 2r, and we're adding an r, so this becomes x to the 24 minus r. So now, and let's put our indices in here, r equals 0 to 12. So now we have to ask, well, what r do we have to put in to get a power of 16? Well, in order to get a power of 16, well, we need to put in r equals 8. So for the x to the 16 term, we need r equaling 8, since 24 minus 8 is 16. So let's figure it out. So the coefficient is going to be 12, choose 8, times 2 to the 12 minus 2 times 8. And we have, is that it? That is it. So this becomes 12 factorial over 4 factorial, 8 factorial, or 8 factorial, 4 factorial, doesn't matter, times 2 to the negative 4. Let's simplify this just a little bit. So this is going to be 12 times 11 times 10 times 9 over 4 times 3 times 2 times 1. And this is over 1 over 2 to the 4. Let's see how much we can cancel out. So I see a factor of 4 in 12, so that becomes a 3. I see a factor of 3 in 12, so that cancels, becomes a 1. 2 in 10, it's become a 5. And can I cancel out any of those 2 to the 4s? I don't think. So I have 5 times 11 times 9, so 99 times 5 is 495, and then divided by 16. So this is our coefficient for the x to the 16 term in our expansion of, what was it, 2x squared minus x minus x over 2. But I just noticed I made a little bit of an error throughout. So let's fix that error. My mistake. It's not going to be big to fix, so let's just do it. So also, I should have said that we have a negative. Let me do it in a different color so you know what I'm changing. I'll do it in green. So this should be a negative x here, which means that I also have a factor of negative 1 to the r, since negative x is the same as negative 1 times x. So I should really include this guy here in my coefficient as well. So let me go ahead and do that. Negative 1, oh, I was using green. Negative 1 to the r. And this is where it's going to stop mattering. We're going to have here a times negative 1 to the 8. But negative 1 multiplied by itself an even number of times just gives you 1 anyway. So our final answer isn't going to change. If we had a odd number, if r was odd, then our answer would be negative, like that, but it's not, so we don't have to worry about it. Anyway, that's how you can use the binomial theorem just to pick out various pieces of a binomial expansion, or you could use this to calculate the entire binomial expansion as well.